take it away.
Right, great, thanks. Just checking again if everybody can hear me, but I assume so. So yeah, I'm going to be talking about about Bayesian and Frequentist Methodology with PyHF. And before we go into all the notebook stuff that I've prepared, we're just going to quickly fix all the terminology. But before we start with, actually, I can't switch my slides. This is amazing. Oh, I swipe. Okay, so I can swipe my slides, sorry. Yeah, before we start with PyHF, I quickly want to talk about HistFactory. So when we do high energy physics, we often look at pictures such as this one. This is one of the Higgs discovery plots from Atlas. And what this kind of shows us is a binned analysis, where we have like events and then we plug them into discrete bins, and then we have different channels that contribute with different event numbers per bin. And HistFactory is a toolbox that allows us to create these bin analyses. And it actually is just this formula. So we have, in gray, our data generating model, where we have, so the bin counts from our bin analysis and the auxiliary data A that depends on two sets of parameters. We have eta, which are our unconstrained parameters, and then we also have chi, our nuisance parameters that are constrained by these auxiliary measurements A. And then the bin counts have two constitutes. First of all, we have Poisson distributed bin counts, where the mean of these Poisson distributions is given by some model mu of eta and chi. And then we also have a product of all the channels and all the bins. And then in red, the second term that contributes to our data generating model are these constraint terms. And what they kind of do is that if I have an auxiliary measurement A, which already constricts the parameter chi, then I shouldn't deviate too far from that prior knowledge. So they kind of penalize this probability model. So if I deviate too far from what I believed chi to be from this measurement before, then I get penalized. So this is what these constraint terms do. And this is the HistFactory model. And this leads us to what PyHF actually is, because PyHF is a pure Python implementation of precisely that model. It supports auto differentiation, and it already has a wide range of frequentist analysis tools. One of them I'm going to introduce on the next slide, but also today we had Matthew's contribution with a PyHF tutorial. So if you're not super familiar with PyHF, you should definitely check that out. And now on to one of these frequentist analysis tools. So this is very basic frequentist analysis, but one thing you can do is you can do a maximum likelihood estimate. So what's the likelihood? It kind of is, so if you have your parameter distribution given data, and then you fix the data, you end up with a distribution just over your parameters. So fixed data, parameters are free, and then you can find the theta hat that maximizes this likelihood. And then this should already give you a hunch of what your true theta might be. So theta hat maximizes the likelihood. And this is just like a really quick check you can do. And that's also what we're going to do in the notebook. And the second statistics explanation you want to do is, of course, Bayesian analysis methodologies. And one thing you really won't get around when you do Bayesian analysis is, of course, Bayes' theorem. And what Bayes' theorem kind of does is, if you have a prior belief here in pink on the, it's the right side, say you have a prior belief on your parameters eta and chi, and then you make an experiment, which is controlled by your data generating model, and then you get observations N, and then you also have A prior observations from your auxiliary measurements that kind of updates to your belief, and then you end up with your posterior belief. So you have a prior belief, then you look at some great data that you took, and this kind of changes how you feel about your parameters. And this is what Bayes' theorem kind of reflects. And of course, we're interested in these posterior distributions of our parameters eta and chi given some data N and A. And also something that Bayes' theorem really allows you to do nicely is to use your prior knowledge from these auxiliary measurements. And that kind of brings us to, so how can we implement this updating Bayes' theorem and use, of course, the PyHF HistFactory implementation as the data generating model. And precisely this implementation Bayes theorem with the HistFactory model that we get from PyHF, that's what the software package that we've been developing, Bayesian PyHF, that's what it's supposed to do. And we do that kind of in 3 steps. So one step that I'm just gonna like skip over is when we build our prior beliefs for the constraint parameters. We can do so in a very smart way where we already incorporate these auxiliary measurements. I'm just going to name drop like conjugate priors here, but I won't go for reasons of time into any depth here. But what this kind of allows us to do is we don't have to do this main updating step with the auxiliary data, because that can be like huge. If you have lots of constraint parameters, you have lots of auxiliary data, and then when we do sampling, this can take a long time. But if we say, okay, if we have a smart way, and we have a smart way to incorporate the knowledge from these constraint measurements already in building the priors for these constraint parameters in closed form, then we don't have to sample there, which saves time and computational cost. So that's great. And this is all part of like this Bayesian PyHF package, building good priors from these auxiliary measurements. But the second step is, oh, sorry, that's wrong. Okay, the second step is for the unconstrained parameters, sadly, there's no smart way to build it because we don't have any prior measurements. I mean, that's what you're doing in this measurement. So you have to make a smart guess and have to figure out what you believe your unconstrained parameter might be. And then we have the priors as ingredients. And third ingredient is this data generating model, which is this PyHF HistFactory implementation. Again, we're just updating with the actual observations, the bin counts, not with the auxiliary data now. And then we end up with our posterior distributions in blue. This is done, yeah, this is pretty much what the software package is about. Okay. Yeah, so Bayesian PyHF, that's a tool to enable the Bayesian methodologies for PyHF models, in addition to the frequentist methods that are already implemented. And the Bayesian analysis tools, of course, we didn't write them ourselves. We're taking them from a software package called PyMC, which implements Monte Carlo Chain Methods for sampling from this prior plus data generating model. And then it gives you these samples from the posterior distribution. And also, after we have put some further effort into developing and testing for stability, we also plan to fully integrate that with PyHF, but this is still a bit in the future. Okay, now I'm not going to click the launch binder because I think, can you follow my screen switch that I'm now online? Can you see my notebook?
Not at the moment.
Okay, so I think I have to stop my screen share and start again in the browser. Okay. Can you see the notebook now?
Yes.
Brilliant. Thanks for the feedback. Okay, on to the hands-on notebook talk. Okay, so we start by just importing all the modules. And important, I'm trying to highlight this part here. We're setting the PyHF backend to JAX, which is one of the autodiff backends, and you'll see why in a second. And then from Bayesian PyHF, the software package, we're importing the 2 functions, infer and plotting, and this should set us up to go. So I brought 2 examples with me today. The first is, okay, so I tweaked it a bit for some reasons, but it basically is a public likelihood that I downloaded from HEP data, which was a Atlas search for displaced laptops. Okay, so that's example number 1. And just a quick recap, sorry, scrolling here. So when we do Bayesian evaluation, I just want to have a quick recap on 2 things. First is, okay, so in this HistFactory model, we had this nominal, this mean of the Poisson distribution, so the bin counts, and they, so the bin counts equal signal strength times some signal plus some background controlling parameters chi, which will be our constraint parameters, times some background. In SNB, like signal and background, that should be somehow theory motivated, but this is how we get like the means of these Poisson distributed bin counts. And then again, Bayes theorem, posterior equals data generating model times prior. Okay, and these are the ingredients that we need for Bayesian inference. Okay, so we're importing here in the cell I just highlighted this workspace that I created. And now that we have the workspace, we can extract the statistical model, which we need for the updating. So can you follow? Sorry, I'm checking stuff, but can you follow what I'm typing?
I can see you typing at the moment.
Okay, that's brilliant. Sorry, that was the last check. So now we have a statistical model. That's brilliant. But we also need observations, and all of that is, all of that is included in this workspace. Probably shouldn't talk a type. And then also, we need to set this flag to false, because I already said that we're not including auxiliary data. We're saving computational cost here. Now we have model observations. What's left are the priors. So for the constraint priors, again, we're not doing anything here. This is all taken care of by the smart way, which I'm not going to explain further here, but we still need to fix the unconstrained prior. And so what do we know? So it's a signal strength, so it's probably positive. So our prior belief shouldn't be like a Gaussian around 0. It should be something strictly positive. So say a half norm. So I have this template here. We're now going to fill in. Okay, so that's the type of prior we're interested in, a half normal unconstrained. But then also we're not super sure like how it exactly looks. So we're going to choose a pretty broad distribution. And then also we should fix the number of draws that we want PyMC to draw. And this number should in principle be way higher, but for reasons of time, we're just going to do 5,000 draws. Okay, and this should have, like, we have a model, we have observations, we have unconstrained priors, and this already allows us to start with the first round of Bayesian inference. So how does that work? So we open a context with this infer module that we imported. And I'm just going to stop talking really quick and just type. Okay. And I'll explain in a second. If I don't have a typo, that should just take a second. Okay, so what are we doing here? So we're opening this like context, and we're submitting the model, the unconstrained priors, and the observations, and then we're sampling with PyMC, and we're sampling number of draws, okay, 5,000, and also PyMC can sample multiple chains, but we're just for reasons of time going to sample one chain here. And as you can see, we're auto-assigning the no U-turn sampler here. That's a certain type of Hamiltonian Monte Carlo sampling, which relies on gradients. And this is why we set the PyHF backend to JAX, because PyMC realizes, oh, we have gradients, great, so we can do HMC sampling, which usually has higher quality sampling chains. And now we have this post data object, which has all the information from, the posterior distribution we sampled from. And here I'm going to highlight that real quick. These are the parameters we just sampled from. And this is something that we can access through this post data object. Okay, but something fun that we can do now that we have this post data object is we can also do posterior predictive sampling. So I'm just going to copy this context here. And then we're going to do what we call posterior predictive. So what that is, I will tell you in a second. Okay, no typos here, I hope. Yeah. Okay, so what we're doing here is we're sampling the expected bin counts from these posterior distributions. And we can do something similar by sampling from the prior distributions. So we're going to call it prior and delete that. And we're going to sample 5,000 draws again. This is super fast. And now we can come to the two plots that I want to show you. So the first plot is comparing, okay, so you should see everything here now, is comparing these posterior distributions from the parameters with the prior parameter distributions. These are just like 3 of them, because 18 would have been hard to fit on the screen. But these are like Lumi and this signature cross-section. These are 2 of the constraint parameters. And here the posterior and prior measurement, they shouldn't really change too much, because our knowledge from these like prior measurements should really be in accord with our new measurement. But for this unconstrained parameter, we actually see that, okay, so we knew it was like close to 0 before because we submitted this half normal, but updating with the observations kind of pushed our belief closer to 0, because of course the signal strength for this BSM signal was 0. Okay, fine. And then also visualizing these predictions is also kind of undramatic. We can see, okay, we had observations 0 in all 3 bins, and we see that the priors and posteriors are close to 0. Fine. Okay, so that was a pretty undramatic example, but that was just to show you like the workflow kind of from HEP data to Bayesian inference plots. So second example is a toy gamma gamma to Higgs workspace that I built, where we just have an exponentially decaying background, and then somewhere in the middle we have a Higgs peak. Okay, and then, okay, so for reasons of time, I already filled that out. Again, we have this cell here. We create the workspace, we extract the model, we extract observations, but now we also extract observations, including these auxiliary measurements, because we want to do a frequentist evaluation. Okay, so that's what we're going to do. We're using the pyhf, and then we're doing this maximum likelihood estimate. And oh no, I didn't execute that. Did I? Okay, sorry. Just need to check that. So I think I might just restart the kernel because it seems that something didn't update.
This is a good point to point out that if you want to have 5 minutes for questions, you should wrap up in 5 minutes.
Yeah, thanks. I'm getting close. Okay. Don't know what didn't update here. I'm gonna check if that works. Okay. There's a typo here. Okay, that's a bummer. I don't know.
I don't think the cell that's under your cursor, I don't think you've rerun it since you restarted the kernel. Don't know if that's important. The one below this one.
Oh, right. Thanks. Okay, should work now. Thank you. Oh, great. That's what I wanted to see. Thank you. So, yeah, so we see here basically the maximum likelihood estimate for the signal strength is 1 because I created this workspace so that we would find a Higgs. But this is great because now in the next step, we're trying to build a prior for the signal strength for this workspace. And I already pre-filled that here. So we know from this maximum likelihood estimate that a signal strength should be around 1. So we're going to choose a gamma distribution signal. So it's like positive because we have a signal strength. It's centered around-ish 1. So this is like a great prior that we can build from this frequentist knowledge we gained. And then, yes, the sampling, okay, I'm going to re-execute that because that's going to be super fast. Again, we're sampling from the posterior distributions. In this case, we just have 2 parameters, which are called like mu, or signal strength. And then I also just added a normalization uncertainty of, I think, like 5 or 10%. And then in the next step, we're going to do similar to the example above. We're going to sample the posterior predictives and the prior predictives. And then we're going to look at the 2 signature plots I'm always making, and then that's that. Okay, so the predictives, again, we're sampling the posterior distributions and the prior. And this plot looks much nicer than the one above, I think. In a second, yeah. Okay, so this is a great prior posterior predictive check, where we see, okay, so the data with the peak in the middle, and then we have in orange our prior beliefs, and then this posterior belief is like really closing in on the data. So that's what we want to see. And this is also a great cross-check if your modeling really was off, because if the posterior distributions would be, for example, more incongruent with the data than the prior predictive, then something of your update probably didn't work. And then also, last plot I'm going to show you is again this correlation plot between the parameters, where we can see that for the mu parameters, so like here we're like really focusing in on this signal strength equals 1, and yeah, that's kind of what we wanted to see. And then also, just last cell I'm going to execute down here. We can see that the mean of this blue distribution, so of this posterior distribution for the signal strength, is 1.07. And if we remember our frequentist maximum likelihood estimate, just going up here, was 1.07. So it can get super deep when you start to like analyze what these numbers actually imply, like how can we compare these Bayesian and frequentist methods. But in principle, it's just like fun to see how fast we can get. Like a hunch that probably for this workspace, the true underlying value for the signal strength is 1. And I think with that, I'm done, and I'd be happy to take any questions. Yeah.
Okay, thank you. Questions? And you may want to keep your notebook up for answering the question.
Yeah, and also I see right now that like what do arviz and Kona basically provide? Great question, because both are like amazing libraries. So arviz and Kona allow you to directly visualize plots for these inference dataset objects. So I'm gonna go to my notebook again. So these objects that you return here, these post data and prior data, these are like specific type of object, and you can just like plug them into Kona and arviz. And like I think for arviz, for example, did I import it? Yes. Like arviz, for example, allows you to directly access your sampling chains. So here we also see that, I mean, it's not super pretty out of the box, but it already, like, you can cross-check also if your chains are nice. And yeah, so they're like both brilliant libraries for like quickly having a visual check of your sampling chains.
Yeah, thank you. Mighty already answered in the chat, but anyway, yeah, thank you.
Oh, sorry.
Looks anyway nice.
Yeah, no, they're like super fast visual checks, and that's great for like a quick feedback loop of if your chains, because sometimes your sampling chains just look horrible, like you have huge autocorrelations, and this is something that you directly see.
Okay, thanks.
Yeah, thanks for asking.
Unless there are other questions, I have one. So the second to last plot was looking to me like a Brazil band, although in different colors.
Yeah, no, it looks like it, but actually it's like we're talking about this one.
Yeah. So you're gonna be
no, but no, so it's not a Brazil band, so it kind of reflects. I mean, what you could do is you could like, because these are like sampling points, like these are just like 5,000 samples that we draw, and you could, in principle, you could lay like 1 sigma, 2 sigma standard deviations around these points. But this is also over bins and not over the parameters. But it it would be nice to see like, okay, so the deviations, like what are the like 1 and 2 sigma bands of these distributions?
Yeah, okay.
That's true.
Luigi?
I was wondering whether there's anything, any way to also quantitatively evaluate the goodness of it. I mean, you're showing here, of course, the posterior predictive check. I mean, visually, is there anything I can do like for getting some number?
So you mean like different ways you can check the quality of your...
Yes.
Yes. So what you can also do is, okay, so a visual check is like these brands are like nice and broad, so that's already good. And then let me, sorry, I don't know if that's the right. Yeah. Okay, and then also you can check the autocorrelation. So that kind of asks like how much do these samples depend on the previous sample, which of course we want to be like as small as possible to ensure that we actually cover the whole parameter space. And what you wanted to see is in that, like, it's really great here that this autocorrelation is within this gray band. And if these would all like peak out of this band, then you would have high autocorrelation, which wouldn't ensure that you're actually covering the whole space. So if your autocorrelation is like big, that's also something that you could correct it by thinning, for example. And then, yeah, I think, okay, this is obviously a bad model that I just made up, but I think also like this check that for your constraint parameters, that these two distributions are similar. That's also like a kind of, yeah, that's also like a good cross-check to have, because you wouldn't want your new measurement to really have such a huge impact on your constraint parameters, because you do believe your constraint measurement. So it should really look like here, where for these two constraint parameters, they're like similar. Yeah, these are just two cross-checks that come to my mind, but then you can also, yeah, and then you can do like calibration checks and so on. And there's like this really brilliant GitHub pages page from Michael Betancourt, where he like kind of talks about this principled Bayesian workflow. That's how he calls it, because there's no like step-by-step how do you ensure that you have good Bayesian modeling, but there are like some principles that you can follow to ensure that your model is like believable in the end. So that paper is linked in my talk, and that's also what we tried to follow when we developed our tools. Yeah, I hope that answered your questions a bit.
Yes,
Thank you for
thanks
for checking in.
Any other questions? I think we have time for just one more.